Hello everybody and welcome to Chapter 2. Chapter 2's focus is on summarizing and graphing data. 2.1 we are not going to cover. It is basically just a review and only contains a very small amount of material. So we're going to jump right into 2.2 for Chapter 2, which is on frequency distributions. So the key concept in this section is that when working with large data sets, it's often helpful to organize and summarize your data by constructing a table. And those tables are called frequency distributions in statistics. Oftentimes, software and calculators are the easiest way to go about doing this, but I'm going to teach you how to go about constructing a frequency distribution from scratch so that you can understand how to construct them, as well as understand what they can tell us about our data sets. So what is the definition of a frequency distribution? A frequency distribution also is called a frequency table. So the purpose of a frequency distribution is to show how a data set is partitioned among several categories. Those categories are also known as classes, and what you do is you list all of the categories along with the number or frequency of the data values in each of them. Now that may sound a little wordy, but let's keep going and you kind of see that it's not really as complicated as it may sound. So here is a frequency distribution. So this is on IQ scores of low lead groups. So here what you see in the table, which is off to the right hand side of the slide, is that you have IQ score in one column and the frequency in the other. The IQ scores that you see listed, 50 to 69, 70 to 89, and so on, would be considered your categories or classes. And in the other column, what's corresponding to them is the number of times that an IQ score in that range shows up within your data set. So for example, from an IQ score of 50 to 69, there were two people in your sample that had that IQ score, and so therefore it's represented in your frequency column. Something else I want to kind of point out to you that's on this slide as well, just beyond the basics of just the basic table, is also pointing out what are known as lower class limits. And these are known as the smallest number that can actually belong to a different class. So for instance, in the 70 to 89 class of IQ scores, 70 would be the lowest number that would be acceptable to be considered part of that class. Whereas in the next class, 90 would be the lowest, and so on. So those are known as lower class limits. In contrast with that are upper class limits. So just like back to the example of the class of 70 to 89 as an IQ score, 89 would be our upper class limit. That's the largest number that can belong to that class and still be considered part of it. Another thing I want to talk about with respect to frequency distributions are what is known as class boundaries. Class boundaries are the numbers used to separate classes, but without the gaps created by class limits. So for instance, if we look at the IQ score class of 50 to 69, and then the IQ score class of 70 to 89, we see that between 69 and 70, there is a missing 1 point IQ score. Where would you put an IQ score of 69.5? Would it go up or down? And that boundary, the halfway point between your upper class limit of one class and your lower class limit of the next class, is what's known as your class boundary. So between 69, which is the lower class limit of your 50 to 69 IQ score class, and your 70 to 89 IQ score class, the midway point between the two is 69.5, and that would be known as your class boundary. You also have what are called class midpoints. These are the values in the middle of the classes, and the way that you can find them is by adding the lower class limit to the upper class limit and dividing by 2. So if we were to add 50 to 69 and divide by 2, we'd find that our class midpoint is 59.5. Similarly, if we added 70 and 89 and divided that by 2, we would find that our class midpoint is 79.5. We also have what's known as a class width. This is the difference between two consecutive lower limits or two consecutive lower class boundaries. So what it's really telling us, and the easiest way to do this, is to take your lower limit from one class and subtract your lower limit from the previous class. And here you would see that the difference between them is 20. Similarly, you could also do it from your upper class limit. So if you took 89 and subtracted 69, you would find that you would still get 20. So your class width, regardless of how you go about calculating it, either using the lower limits or your upper limits, you'll still get the same class width. Okay, so now that we've talked through frequency distributions, we've talked through how to create a frequency distribution, and really all a frequency distribution is a table. And we've talked through some of the terminology to define various aspects of the table. Let's talk about the reasons for why we may want to construct a frequency distribution. The first and foremost reason is that large data sets can be summarized, and easily. The next is these frequency distributions allow us to analyze the nature of data, and we're going to see that coming up. And finally, based on these frequency distributions, we have a basis for constructing graphs. And as we're going to see in the rest of this chapter, graphs are a pretty important way to visually show your reader what you're hoping to them to walk away with as the conclusions of your statistical study. So, let's talk about the actual steps for constructing a frequency distribution. The first thing is that you're going to determine the number of classes. You don't want too many and you don't want too few. The general rule of thumb is somewhere between 5 and 20 classes. Then you're going to calculate your class width, and you always want to round up. So your class width is going to be your maximum value that will fit within a class minus your minimum value divided by the total number of classes that you have. Then you're going to determine your starting point. You're going to choose the minimum data value or a convenient value that's below it as the first lower class limit. Then you're going to use that first lower class limit along with the class width that you've already calculated to proceed to list the other lower class limits. So once you list the lower class limits in a vertical column, then you can proceed to enter the upper class limits based on the class width that you've determined for your frequency distribution. And finally, you're going to take each individual data value and put them in the appropriate class to get your actual frequency of data values that fall within that class. I've also handed out a worksheet that goes through this, and I would be happy to spend time reviewing that to make sure that everyone knows how to go about constructing a frequency distribution. But definitely don't overthink it. It's fairly straightforward. You need to construct your table and then fill in the appropriate information. And although this slide is fairly wordy, that's really what it's asking you to do. Okay, so we've talked about frequency distributions, but a lot of the time, instead of a true frequency distribution, statisticians use something called a relative frequency distribution. And basically all this is the exact same class limits as the frequency distribution that we already saw, but the frequency of a class is replaced with a relative frequency, which is also called a percentage. So when you think relative frequency, think percentage. So in order to calculate a relative frequency, you're going to take the class frequency and divide it by the sum of all the frequencies. And then you'll multiply it by 100 to turn that into a percentage frequency. So let's see how that works. So here is our same IQ score table that we had in the previous slides. Here's the frequency that we've already calculated and was given to us in the previous slides. And now we're going to tell you roughly out of 100% how much each class is represented. So with a frequency of 2, your 50 to 69 class is only 2.6% of your overall data. Whereas your 70 to 89 class with 33 as your frequency is 42.3% of your data, and so on. And if you were to add all these relative frequencies together, they would add to 100%. Because if you're capturing all the data, then it must add to 100% by definition. We're going to see that many times during this course, so please do begin to think about percentages and how to interpret percentages, because we will be seeing these moving forward as well. We can also, although this is a little less important, so I'm not going to spend a ton of time on this, but let's talk really quick about what a cumulative frequency distribution is. All that is you take the frequency from your first class, you're going to add it to your next class to get your cumulative, then you're going to add that to your next class to get your cumulative, and so forth and so on. So again, I'm not going to spend a lot of time on cumulative frequency distributions. They really aren't all that helpful. I'd really rather you focused on the frequency distributions and the relative frequency distributions. Okay. Another thing that I want to introduce in this chapter is frequency distributions can be used to understand data. So we're going to talk a lot in the later chapters in this course about reference to data with a normal distribution. And what I want you to think about when you think of a normal distribution, think of the key characteristic of it being that it has a bell shape. So what that means is that the frequencies start low, and then they increase to 1 or 2 high frequencies, and then they decrease again to a low frequency. And the distribution of this bell shape should be approximately symmetric, with frequencies preceding the maximum being roughly a mirror images of those on the other side. A good way of thinking about it is if you were to hold your arms out straight from your body and imagine a line that goes from your fingertips on one side to the top of your head and then down to your other side, that actually makes a bell-shaped curve. You're going to slowly increase, reach a peak, and then come down the other side. So that's a good way of trying to remember what a bell-shaped curve looks like. Your body's also a good example of a bell-shaped curve because both sides are symmetrical, which is the same thing with this bell-shaped normal distribution that we're discussing. Okay, a couple of other things to talk about. Let's talk about what gaps mean. So gaps is the presence, well, let me back up. The presence of a gap in your data can show that you have data from 2 or more different populations. So what I want to I don't want to spend a ton of time on gaps, but I want to give you a good example that illustrates it well. So on the next slide that we're going to see, and here I'll show it to you here, here is a frequency of pennies, and pennies were weighed. And you can see that the different classes, so 2.4 to 2.49 grams, and so forth and so on. And you can see the frequency of pennies that fell within that. And something that you might notice here is that you have a gap right here. So from 2.6 to 2.89, there were no pennies that fell into those weight ranges. Now, normally you may just chalk that up to chance, but in the case of a major gap like this, it actually suggests that the data might be from 2 or more distinct populations. So let's try to understand why that is. So pennies that were made before 1983 are 95% copper and 5% zinc, whereas pennies made after 1983 are 2.5% copper and 97.5% zinc. And so really what you're seeing in this diagram is that you have pennies that were pre-1983 and pennies that were post-1983. And so actually by putting your data into a table like this, it allows you to be able to visually see this very quickly. Okay, that's going to end section 2.2 on frequency distributions. Coming up next, section 2.3 on histogram.